Welcome to the first lecture in your third week. This time we are going to talk about operators in quantum computing. Remember that we talked about vector spaces and matrices. We know that matrices are linear operators. They are operators on our vector space. Since vector spaces form the state space by the first postulate, our guess is that matrices will be the operators on the state space. So these should be our operators. Our operators or gates like AND or NOT and things like that. It turns out the intuition is right but not completely right. Only some special kind of matrices are allowed to be operators. These are the only operations we can perform in quantum computing. To learn about those, we need to cover some more linear algebra. So let's just dive into it. This video will be about eigenvalues and eigenvectors. I assume that you have seen these concepts before and are familiar with it. So I will just revise these concepts and emphasize points which will be needed later. Remember, generally when we talk about matrix, we say that it is element of LV, W. This is the space of all linear operators from the vector space V to vector space W. When we talk about eigenvalues and eigenvectors, we are interested in only square matrices, and so now we will assume that we are talking about M element of LVV, which in shorthand we write LV. So this is the space of all linear operators from V to V. What is an eigenvector? Given M element of LV, a vector V in this vector space V is called an eigenvector if MV is equal to lambda V. When we multiply, we get a stretch, and every coordinate is stretched by this factor lambda. This stretch factor is called the eigenvalue of eigenvector V. This is pretty basic and I'm sure you know about this. Let's look at few more properties of these eigenvalues and eigenvectors. Let me ask you a question. When is alpha V plus beta W also an eigenvector? We are given that V and W are eigenvectors. If this is the case, what can happen? So suppose V is an eigenvector with eigenvalue lambda 1 and W is an eigenvector with value lambda 2. In that case, M of alpha V plus beta W is equal to alpha MV plus beta MW. This is alpha lambda 1V plus beta lambda 2W. This is some constant times alpha V plus beta W only if lambda 1 is equal to lambda 2. You can convince yourself of that, and if this is the case, then this blank also comes out to be lambda. This gives us the statement that alpha V plus beta W is in itself an eigenvector if and only if V and W had the same eigenvalue. Not obviously all vectors are eigenvectors, but if two of them were eigenvectors, if we knew V and W were eigenvectors, There any linear combination will be an eigenvector if they are from the same eigenvalue. This helps us. This tells us that the set of all vectors which are the eigenvectors of lambda, eigenvalue lambda. So let's take all vectors V such that V is an eigenvector with eigenvalue lambda. Again, a matrix M is fixed. If this we already know, if this, think of this set, then this set S is closed under addition and scalar multiplication, the two defining properties of a vector space. That means if V is element of S implies alpha V is element of S. If V comma W is element of S, then V plus W is element of S. Other way to say it is that for any alpha and beta, alpha V plus beta W will be in S. This is the defining property of a subspace. You should know this. What we have shown here is that the set of all eigenvectors with a single eigenvalue. So you fix an eigenvalue and look at all the eigenvectors corresponding with it, they will form a subspace. So let's say the single eigenvalue was lambda, then the subspace is actually called lambda eigenspace. These are the three words you have to remember: eigenvalue, eigenvector, and eigenspace. For some matrices, the eigenvalue could, for a particular eigenvalue, you only might have one eigenvector and its scalar multiplications as eigenvectors. So eigenspace will have dimension 1, but in general, your eigenspace could be much bigger. Remember, we are talking about vector spaces of the form Cn, and the subspace always looks like seed the M such that M is less than N. So if we look at all the eigenvectors of a particular lambda, a lambda eigenspace, it will look like seed the M for some M less than equal to. This is how our eigenspaces will look like. We also know how to find lambda. This is again a recapture of things which we have studied before. Determinant lambda I minus M. This is called the characteristic polynomial. And we know that the roots of this are basically the eigenvalues of M. Here det is the determinant. I am just revising things which you have already seen at some point of time. We are talking about complex numbers. In the case of complex numbers, notice that we are going to have all n roots. If M is n cross n, then determinant lambda I minus M will have n roots. It's a polynomial with degree n, so we will get n roots in complex numbers. We also know another thing. If P is a full rank matrix, full rank means no vector, non-zero vector V exists such that PV is equal to 0, or we can't write the linear combination of columns to be 0. If P is a full rank matrix, then I'm sorry, I shouldn't write P inverse, M inverse, but P inverse MP and M have the same set of eigenvalues. This P inverse MP, we should think of it as some sort of basis change, not necessarily a nice one. I will talk about the nice basis change later, but P inverse MP, we should view it as M itself, but looking at it from a different viewpoint. That's the only way. The proof of this is not very difficult. We will show that if we have an eigenvector for P inverse MP, then it will be an eigenvector of M. Similarly, if we have an eigenvector of M, then we will have an eigenvector of P inverse MP with the same eigenvalue. So let's start. Suppose V is an eigenvector for P inverse MP. That means P inverse MPV is equal to lambda V. Multiplying by P by both sides, this shows that MPV is lambda PV. This is very simple. This shows that if V is an eigenvector for P inverse MP, then PV is an eigenvector for M. The opposite side is very similar. What we can show is that if V is an eigenvector for M, then P inverse V is an eigenvector for P inverse MP. This is again not at all difficult, and I will leave the proof to you. This shows the complete proof. So we will remember that P inverse MP and M are similar matrices, just looked differently. One, I'm looking at M in a different basis, then it will become P inverse MP. Just notice, why do we need P to be full rank? Think about this question. Pause the video. There is a simple answer to it. The answer is P inverse should exist. Otherwise, P inverse MP does not make sense. And you can actually see that this condition is necessary by the example of this matrix. Let me take this diagonal matrix which has 1 and 2 in the diagonal. You can easily show that the eigenvalues are 1 and 2. Let me take a matrix which is not full rank. And now, if I look at this, then even if I take the pseudo inverse of this matrix, which will again be 1 0 0 0, you will see that this 1 0 0 2 1 0 0 0 will not have same eigenvalues, will not have 1 comma 2 as eigenvalues. This is an easy thing to verify. So pseudo inverses will not work. If you don't know about pseudo inverse, don't worry. You just notice that P inverse need to exist to make this theorem work. This was a small introduction to eigenvalues and eigenvectors. In the next video, we will see spectral decomposition, which will be very helpful in doing a lot of linear algebra and quantity.